Hi everyone, this is Jayashree. We continue with the previous topic, that is PID controller, that is a proportional integral and derivative controller. Right. We said the process is dynamic. So all the process to be controlled is dynamic. It changes with the time. For example, if we take a power system, the voltage level and frequency is changing dynamically for each and every second. It is changing. So the system is a dynamic system. So we have to look upon what is the present value, what is the previous value, past value, and future value to control the processor, to control the system. Right. So we can split the controller into three ways. One is based on present state, and then past inputs and the previous values. So we can split this into three ways, right? And future values. So if we are taking, we have to take the set value, that is measured value, that is actual value. This MV is measured value. We have to take it from the present input and we have to give it to the controller. That controller compares a set value, set point with the measured value. The error signal is generated. That error signal is sent to the controller. Right. The controller converts the error signal into its required control input to the process. For example, if you wanted to control the temperature of a furnace, means the error signal is to be converted into the corresponding valve position. So that is the value U. So the value U represents the valve position. Mm, right, right. Then present value. So this part of controller is only concerned with what the error is now. So what is the error now? Presently, what is the error? Okay, so we have to take that as E. Then let us take a simple law. Let the control signal be proportional to the error. So what is this my control signal? U equals to Kp into E. So E is my error signal, Kp is my proportional gain. So if you multiply the proportional gain constant into the error value, E will get the control signal to the process. Okay, we get the value U from the controller, and that value U signal is given to the process control. Right. So this is what referred to as a proportional controller. The control action at any instant is the same as a constant times the error at the same instant. The constant Kp is the proportional gain, and this is the first of our controller parameters. So Kp is proportional gain that is derived from based on the present error, right? So here U equals Kp into A. The next one is the proportional controller enough? Is it enough? The proportional control, no. We have to consider the steady state error also. Usually, there is an before the present error, always there is an error in the system. That thing we have to consider as a steady state error. So intuitively, it seems like it should be fine on its own. When the error is big, the control input is big to correct it. Right. As the error reduced, so does the control input. But there are some problems. If we take on a simple pendulum, otherwise controlling the water flow in a tank, there is always a steady state error that also need to be considered. So solving steady state error in the past, how to calculate the error in the past? So see, look into this picture here. The input is a step input, so the value is constant. If the system is getting disturbed, the value is oscillating to and fro. The value is oscillating to and fro. So that equals to R divided by 1 plus KB. So reference input, that is my reference input. Then for a particular time, the output is oscillating, and after a particular time, it comes to steady state. Okay. That error ESS, it is not nearing to that input value. The actual output is differing from that input value. That thing we call this a steady state error. Okay. To calculate that, to compensate here we are, it is a continuously varying quantity with respect to time. So, integral calculation based on the sum of error. Okay, so that is the area behind the curve. So, this area and the area that is shaded area, one is set point, then one is power process variable. So, by calculating the area of this errors, we can define what should be the error constant, right? So here it is a continuously varying quantity. So here, so we are introducing on integral constant u equals ki integral 0 to t e2 into d2. So that is my integral gain constant ki. So ki is integral gain. Okay. Thanks for watching. We'll continue in the next video about derivative controller and the combined PID controller. Thank you.